So let's take a look at these different types of failures. So within this, as we're looking at these different types of failures, we want to ask ourselves a few different questions. The main question we want to ask ourselves is what in a design is going to constitute a failure? So what are we considering as failure for the design that we're working on? Now, within that there, we can also ask ourselves some sub-questions here of what are the mechanical outcomes, what can affect these mechanical outcomes, and then also, are there some non-mechanical failures? What might these non-mechanical failures be? So first, let's take a look and define what are mechanical failure outcomes right here. So what are some of these mechanical failure outcomes? Well, some of these could include fracture. It could be yield or permanent deformation, excessive deformation, or buckling. So these are all types of mechanical failure outcomes right there. So if we think about these, let's just go to a simple case. We're thinking about a tensile test where we got a dog bone specimen that we're pulling in tension right there. Well, these are all the mechanical failure outcomes of that part right there, our dog bone specimen right there. So we could have fracture. We could see that, we could observe that, we could look at our stress strain curves to determine the fracture there. We could also have yield or permanent deformation. So again, that's something we could look at our data from that individual part to determine, okay, did it go past the yield point there? Do we see that permanent deformation? Or when we unload it, does it return to its shape, its original size and shape? So that right there could be our determination of failure right there. If we load this part, and it seals, it yields, and it has permanent deformation. When we unload it, it doesn't return to that same size and shape, then that could be a failure for us, because maybe it's a part that needs to be loaded and unloaded, loaded and unloaded multiple times as its function within the whole system or the whole product right there, so that if there is yielding occurring, we're considering that to be a failure for this individual design right there. Other designs, maybe that yield is not important, is not considered a failure right here. But this is one right here, what we're talking about now for mechanical failure outcomes right there, where if you do have that permanent deformation, that could be considered a failure right there. Another one could be excessive deformation. Maybe if you go past a certain point, there may be a percentage right there that if it deforms past a certain point right there, that's going to be considered a mechanical failure right there. And then buckling also is another one right there, and that's a pretty straightforward one. If you see buckling going on, you can even observe that occurring in most cases right there, that would be another example here of a mechanical failure outcome. So looking at this picture right here, one thing that we do want to think about with these mechanical failure outcomes right here is not only how it affects the individual part, but how it affects the system as a whole. So even if one part on something, a plane right here, fails, how does that affect everything else within that system right there? Does that cause other things to fail and a whole catastrophic failure, or does that just one part fail and there's redundancy in the system and it's not as crucial? So those are all types of things that we need to consider within this design process. So continuing on with our topic of these different types of failure right here, let's take a look at mechanical failure outcomes and what they're affected by right here. So they can be affected by crack propagation, fatigue, creep, surface damage, surface wear, and environmental conditions. And within the environmental conditions, we're taking a look at things like corrosion and chemical effects, thermal effects, light, radiation effects, and biological effects. So again, relating this back to our design process, how do we design for these type of things? So we can think of each of these, think of how they occur for our individual product, part, or system right here, and think about how we could make things, how we could adapt things, change things in order to reduce these right here. So if we're talking about, let's just say, surface damage right here. Now this is something we want to consider where if a part's being used over and over and over again, or if we're talking about that airplane again right there, you've got wind and you've got surface damage from particles in the air, from rain, from dirt, dust, all those types of things, and you're having that surface damage right there. Well, what could we do to protect that surface? Is there a coating that we could put on and apply? Is there a type of cleaning system that we can use in order to protect it a little bit better? Is there things that can be replaced? Is there a skin that we could use over the outside stuff? Is there a different material that we could be using that's not going to be damaged as quickly? So all of those are factors that we need to consider when we're talking about this. So this is why we need to stop and think. If we're talking about this topic right here of mechanical failure outcomes and what they're affected by, well, if we understand what they're affected by, how can we address each one of those issues right there with, again, a design criteria, a different type of material, another creative thought right there, like we're saying with these skins and things like that. How can we go through and modify these to reduce that? And I know we've talked a lot about how people are intended to use this product right here and how sometimes they use it out of the intended use, and that's definitely something we need to design for. But the thing that we also really need to design for as well are these environmental factors right here. And a lot of these are going to be out of our control. Now we can take a look and say, well, this is typically going to be used in this climate right here, so those, thermal effects are going to be great importance because we're going to be in a warmer climate. Or maybe we're going to have this in Alaska and thermal effects up there because it's going to be really cold. So you might have extreme and cold due to where the product is going to be used primarily. But you got to think of, well, maybe somebody else is going to use it elsewhere outside of that type of environment right there. So you need to have a range that this can, or at least understand the range of temperatures that could affect this right here. Same type of things right here, light and radiation effects are something that are environmental that we have little control over. Some of these right there. You know, is it going to be out in the sun a lot? Is it going to be fading a lot? And is that fading of it right there going to deteriorate anything, or is it just aesthetic? And then we got to think about the environment right here. Is it a corrosive environment? Are we going to be near the ocean? Is there going to be salt that could affect it? Maybe this is not even just the ocean, but maybe this is in the Northeast where we have brine that we're using there, and it's part of a car right there. And all of a sudden, you're going to have that salt water right there coming up on that part right there, or that system right there. And is that going to be an effect right there? So these are all things that we got to consider that may be out of our control, but we need to consider them within the design process, and they could lead to these different types of failure, in particular here, the mechanical failure outcomes. So these are things that can affect that mechanical failure. A lot of the loading we're dealing with within this module here, and within this course right here for that matter, is going to be dealing with our static loading right there. So with our static loading, let's take a look at some of the static failure theories. Now, a great resource for the static failure theories right here is our typical stress strain curve. We can get a lot of information from the stress strain curve right here. Now, whether this is something that's given to you from the manufacturer, and you have this information that you can take a look at for these different types of materials, or if this is something that's you've developed from testing. So maybe it's a product, or just a sample, a dog bone specimen right there that you're looking at right there, and you want to take a look at the mechanical properties of it right there. Well, the stress strain curve is a great way to do that. So a lot of times we're doing a typical tensile test right there. We get our raw data in that force displacement mode right there. So with that there, with our dimensions, we can go from there and create our stress strain curve with our basic equations right there for stress and strain. We can use that information from dimensions, our force, and our displacement as well. From that raw data, we come up with a curve that looks like this. And in particular here, let's take a look at the material and like, is it a brittle or is it a ductile material? And within that there's a couple different options there. So if we know this material is either brittle or ductile right there, that could help us in our design process decide like, yeah, this material is going to be a little bit too brittle, let's take a look at a different one, or this one's going to be way too rubbery for what we need it for. You know, we need to go with something that's going to be a little bit more towards the brittle side of that right there. So we look at this right here, and if we're talking about our stress strain curve related to this right here, if we're talking about brittle material, we can see a very, very steep curve coming up right here for that type of brittle material like that right there. So with this right here, what we know from that there is it's going to be a very little bit of strain for quite a lot of stress. We're going to see a lot of stress on this object right there and not much strain right there. And it's going to be a real brittle, quick failure right there once we get up to that loading right there. It's not going to change. It's not going to actually deform or strain very much right there. So the other type right here, let's see ductile. Now we have a little bit more of a curve right here heading in towards the strain region right there. So not quite as much stress right here, but we're seeing a lot more strain going on. Then we also have the case right here. We can see the shape right here. Now we can see we have necking occurring going on within this curve right here for this ductile material right there with necking. And then we have this elastomeric rubbery material right here, which we can see follows a curve like this on our stress strain curve right there. So a lot of information that we can determine that we do know when we're asking ourselves, what do we know, right from our stress strain curve for these different types of materials right here. We're talking about the ductility. So now I want to take a minute here and do a little bit of review of Moore's circle for plane stress right here. So this relates back to your Mechanics of Materials course, your ME14 course right here. So what we want to take a look at here is actual Moore's circle. So with the physical significance of Moore's circle for a plane stress that's established. So we have one of these that is established. It may be applied with a simple geometric considerations. So critical values are estimated graphically or calculated right here. So we can estimate these graphically or we can calculate them there. So Moore's circle gives us this estimate, this visual graphical estimate right here in order to get these values right there. So if we have a known state of stress right here, plane stress right here, whether it's our sigma x, our sigma y, or our tau xy, we can plot the points x and y and construct a circle centered right here at this value C there. So we have this relationship here that our sigma average, our average stress right here, is equal to our sigma x plus our sigma y over 2. And we can go back up here. We can see this is our sigma y. This is our sigma x right there. So we can see these for our element right there. So it's our sigma x and our sigma y right there. And our radius right here, our R value right here, is equal to the square root of that sigma x minus sigma y all over 2 squared, plus our shear stress, our tau xy here squared. So we can come down here, our tau xy on our graph. This is our tau xy on our graph right there. Now we can all then obtain our principal stresses at A and B. So we have these at the two outer sides of the circle right there. There's our A, there's our B, and we can see if we go right here from our 0 point right here to our origin right here, out to A, this is our sigma max, and then out to B, this is our sigma min right here. And then we have this relationship that we can see here, that our sigma max and sigma min is going to be our sigma average right here, that we calculated from this right here, plus or minus our R value, which is obtained from this expression right here. So continuing on with our failure theory here, if we want to predict failure, if it's going to occur, one thing that we can do is we can compare the results for failure or yield in a tensile test to the state of stress right there. So that's why it's important to take these tensile tests right there and we compare that to the state of stress right there. From that, we can determine the likelihood of failure or the yield in the element to be designed right there. So this is something we could do actually developing it, and in our prototyping right here as we're making out these samples, test and compare from the tensile test right there and go ahead with our design process from there to tweak it to meet the correct specifications. Now we can go back and show this graphically on an axis of principal stress right here. And sometimes this is useful to get a visual of this to actually look and say, oh yes, we are within this, no we're not within this right there. So going back to material behaviors right here with failure theory, what material behaviors are going to require this right here? Well, we can take a look at normal versus shear strength, and we can also take a look at compressive versus tensile strength. And as I mentioned right there, even with that core sample and our concrete decks, sometimes we want to look at both of those because you have both compression and tension going on. Think about a bridge deck, the way it's loading in 3-point bending. Sometimes it's in compression, sometimes it's in tension. Go back to even some of our previous courses right there where we talked about that with 3-point bending. If you look at a beam in 3-point bending right there, if it's going down like this in the center, all of a sudden the bottom of that beam is going to be in tension and the top of that is going to be in compression. The same applies for a bridge deck right there, where you're going to have certain portions of it in compression, certain portions in tension, and it could be cyclic loading as cars are driving over that, and it could be going back and forth, putting the top in compression and tension and the bottom in compression and tension as well. So that's something that is interesting to see right there, is comparing the compression versus tension results. So now let's talk a little bit about the yield criteria for ductile materials under plane stress. The failure of a machine component subjected to uniaxial stress. We're just looking here as we can see this structural element right here under this uniaxial stress. You can see there's our load P and our load P prime. This is going to be directly predicted from an equivalent tensile test. So that makes sense right there. That's a typical setup for a tensile test right there. So the thing we want to think about now is that the failure of a machine component subjected to this plane stress cannot directly be predicted from the uniaxial state of stress in a tensile test specimen. So not directly, you cannot predict it directly from that. Now, oftentimes it's going to be convenient to determine these principal stresses and to base the failure criteria on the corresponding biaxial stress state. Now this failure criterion is going to be based on the failure of the mechanism of the failure. So this allows comparison of our failure conditions for a uniaxial stress test and a biaxial component loading. So when a structure element or a machine component is in a state of plane stress, like we have here in A, so A is a stress element referred to our coordinate axis right there, it's convenient to use one of the methods developed earlier in earlier modules that we've seen there in order to go through and determine the principal stresses, our sigma A and our sigma B, at any given point right there. So we can see there's our sigma A, there's our sigma B right there for our stress elements referred to this principal axis right here. So then our material can then be considered to be in a state of biaxial stress at that point. Now, since the state is different from the state of uniaxial stress, it is not going to be possible at this point to predict from such a test whether the structural element or machine component under investigation will actually fail. Next, let's take a look at the maximum shearing stress criteria right here. So one thing to think about as we're looking at this is the structural component is safe as long as this maximum shearing stress here in yellow, our tau max right there, is less than our maximum shearing stress in a tensile specimen at yield. So our tau sub y right here. So we have this relationship right here where our sigma y is the yield strength of the test specimen right there. So our tau max must be less than our tensile test specimen yield right here, our tau sub y, which is equal to our sigma y right here, which is our yield strength of the test specimen divided by 2. Now, consider the case here where we have our sigma A and our sigma B with the same signs. So we come over here to our axis, there's our sigma B, there's our sigma A. So if we think about this in terms of an axis, where would these both have the same signs? Well, they'd have the same signs in this coordinate and this coordinate right here. They'd both be positive up here, they'd both be negative down here. So for that case where they both have the same sign right here, then our tau max is going to be equal to the absolute value of our sigma A over 2, or the absolute value of our sigma B over 2 right there, which needs to be less than our sigma Y over 2 right there. So now what happens for the opposite case right here? Well, if our sigma A and sigma B have opposite signs here, so they're in this coordinate over here, or this coordinate over here, where they both have opposite signs right there, then we have this relationship here that our tau max is equal to the relationship here of our sigma A minus our sigma B, take the magnitude of that divided by 2, which is still less than our sigma Y over 2, again, where our sigma Y is this yield strength of our test specimen. Now, the way we can use this hexagon up here for maximum shearing stress criterion graphically to visualize this here is what we can think of as if this point falls within the area shown. So this is the area shown right here, that shape right there, that hexagon that we're talking about right there. If it falls within that shaded area, the structure is considered to be safe. So that component is going to be structurally safe right there. But if it falls outside of this area right there, then the component fails as a result of yield in the material. So that's how we can utilize this graph right here as a quick visualization to see if a component is going to be safe or fail. Let's look at the yield criteria for ductile materials under plane stress. In particular, let's focus on the maximum distortion energy criteria. What this criteria states here is that the structural component is safe as long as the distortion energy per unit volume is less than that occurring during a tensile test specimen yield right there. So that's our relationship right there we need to meet in order for this criterion to hold true and for our structural component to be considered safe. Now, this criterion is based upon the determination of the distortion energy in a given material, so we need to calculate that. This energy is associated with its changes in shape in that material as opposed to the energy associated with the changes in volume of the same materials. We're looking now for our changes in shape right here. This is also known as our von Mises criterion. What we have over here on the left in this figure is our von Mises surface based upon this maximum distortion energy criteria right there. So we now see, okay, there's our center point O right there. We have our two axes. We have our sigma A and we have our sigma B, where our sigma A and sigma B are our principal stresses. And we can also see we have our sigma Y, our negative sigma Y right there, where that's our yield. And we can see now we have this area right here that we need to fall within for this criteria. Our governing equation for this relationship is given as a derivation of the equation 7.25 in our textbook. We have 1 over 6g, where g is the modulus of rigidity, times now our sigma A, which is the principal stress, squared, minus sigma A, sigma B, plus our sigma B squared. So that's just a combination of our principal stresses there. And this needs to be less than, that's our u sub d, this needs to be less than our u sub y, which is defined as 1 over 6, times now we have our sigma y, there's our yield right there, squared, minus sigma y times our 0 plus 0 squared right there. So again, our u sub d right here, this is that distortion energy per unit volume. So that brings us back up to that statement here for this equation here. Our u sub d, or our distortion energy per unit volume, is less than, there's our less than sign right there, our u sub y right there, which is the tensile test specimen at yield right there. Now I want to take some time and discuss brittle materials. In particular, let's take a look at the fracture criteria for these brittle materials under plane stress. So if we're running a tensile test, we realize that the brittle materials are going to fail suddenly or through a rupture or fracture. Now this failure condition is characterized by our ultimate strength, or our sigma sub u. If we come down now, we can see our maximum normal stress criteria, which states that a structural component is safe as long as the maximum normal stress is less than our sigma sub u here, that ultimate strength of this tensile test specimen. So we can see over on our diagram here, we have our Coulomb surface for a maximum normal stress criterion, and we have our sigma A and our sigma B. So if we come back over here for sigma A and B, this is going to be our maximum normal stresses. So those are characterized by those two axes there, and they need to be, recall here, less than our ultimate strength. So we have out here in the square our sigma u and negative sigma u to show our ultimate strength there. So what this is saying is that the absolute value of our sigma A right here needs to be less than our sigma u, and our absolute value of our sigma B axis right here needs to be less than our sigma u, or our ultimate strength. So now let's take a look here at our maximum normal stress theory. So here we're going to do is we're going to perform two different tests. We're going to perform a tensile test and a compression test as well. So for each of these, we're going to define an ultimate tensile and an ultimate compressive strength right here. And we're going to represent that graphically. So over here, we can represent that right here. Here is our uniaxial compression and our uniaxial tension test right there. So here is our S sub UC, our ultimate compressive strength, and S sub UT, our ultimate tensile strength right there. So now we can see this is our sigma axis right here. There's our tau axis right here for normal stress down here and our shear stress right up there. So now what we can see from this representation here, so we have both those informations showing those ultimate strengths for compression and tension as a visual representation on our Mohr circle right here. So our principal Mohr circle must lie within these bounds to avoid failure. So these bounds are on either side. I put these two right next to each other like this right here for tension and compression. So in order to avoid failure, it needs to rely on these bounds right here. So let's do that here. We'll do our first one right here. And we can see that this does lie within those two bounds right there. So we don't have to necessarily say there is going to be failure for that one now. But now if we do this one here, this does not lie. You can see this edge of this right here does not lie within those bounds right there. It goes on the outside of those bounds right there. So therefore, that's potential for failure right there. And this is a good graphical, easy way to represent this using Mohr's circle. So going back to our maximum normal stress theory right here, let's plot this on a principal stress axis right here. So there's again our ultimate compressive strength, our ultimate tensive strength right there. Then we can see now we have sigma 2 up here right here. Now our ultimate tension and ultimate compressive strength right there. And this is for a biaxial stresses. So for example here, our sigma 3 is equal to 0 and sigma 1 and sigma 2 must plot within this area to avoid failure. So we need to make sure that sigma 1 and sigma 2 plot within this to avoid failure right there. So for our application and loading conditions, we can plot a point on this figure right here. So we can use this as another way to visualize this and represent it to determine if we're going to have a failure. So we can see right here, inside the box right here, as long as we're within this right here, there's no failure. But if we're outside of the box, then there is failure, and that's where, again, we want to go back and redesign. So this is why I like this here. It's a quick visual graphical representation that we can utilize, again, using maximum normal stress theory right here to determine, maybe I need to redesign it. And a redesign could be dimensions, could be material, could be loading, all those type of things that we talked about in the design process right there. But if we're outside this right here, it's a way that we can quickly see, yeah, we're outside of this box right here. There's probably going to be a failure going to occur, so we need to go back and do a redesign. So the maximum normal stress theory is also referred to as here called our maximum principal stress theory, which makes sense from what we're looking at from our graph over here. And it's also referred to as our Rankine criterion as well. So these are two other terms you may hear referring back to our maximum normal stress theory that we just discussed. So continuing on with our maximum normal stress theory, let's take a look here for 3 dimensions right here. So we have this cube representation over here. We have our ultimate or our yield strength surfaces right there. So we have our sigma 1 plus and minus y, sigma 2 plus and minus y, and our sigma 3 plus and minus y. And how those relate back to this cube over here is you can see this bottom surface right here is represented by sigma 2 is equal to negative y right there. So this is our sigma 2 axis right here, and we can see this is down here, that bottom surface right there of this right here of a negative y right there. Whereas we have up top here in our sigma 2 axis, there's our top surface right here, which is our sigma 2 of a positive y. Now the same thing for sigma 1. If this is our sigma 1 axis, we have this surface over here, which is our sigma 1 is positive y, but then we have this surface over here, which is our sigma 1 of negative y. Then we can take a look at our third axis right here, our sigma sub 3 right here. So here's our front surface right here for sigma 3 on our cube right there, and that's our sigma 3 is equal to y. Then we have our back surface right over here, which is then going to be that back surface is sigma 3 is equal to a negative y. Next, we're going to move on to the topic of stresses in our thin-walled pressure vessels. So these thin-walled pressure vessels provide an important application for the analysis of our plane stress. Since the walls offer little resistance to bending, it can be assumed that the internal forces exerted on a portion of the walls are tangent to the surface vessel. So the resulting stresses of the element of the wall will be contained in a plane tangent to the surface of that vessel. Continuing on with our stresses in these thin-walled pressure vessels, now let's take a look at this pressurized cylindrical vessel over here on the left. So within this here, we can break this down into sigma 1 and sigma 2, which are our hoop stress and our longitudinal stress for this, and deal with each one of these stresses separately. So this is a cylindrical vessel with our principal stresses. Our sigma 1 is the hoop stress. So we come up here, there's our sigma 1 right there. That's our hoop stress right there. And our longitudinal going like this here is our sigma 2, the longitudinal stress right there.
So let's take a look at our hoop stress, our sigma 1 first. Now the easiest way to do this, we'll cross-section this here and we'll come up with our free body diagram in order to determine the hoop stress for the cylindrical pressure vessel. So if we go to our free body diagram, we can see it was our sigma 1 times our dA right there, and we have our sigma 1 dA right there, and then we have our pressure times the differential area right there. So what we want to consider now, let's do out our equilibrium equation. So summation of forces in our z direction right here for our hoop stresses. So if we're going in our z direction there, we can look at our free body diagram and say, okay, what forces do I have acting in my z direction? Well, I do have my sigma 1 acting in my z direction right here. So my sigma 1 dA is going to be that force right there. So there's our sigma 1 right there, and it's the equilibrium equation, so the summation of all the forces are equal to 0. Sigma 1, now dA is our area. So what is our area right here? Well, we can say, well, for our area right here, we have our delta x, and we have this thickness of t, but it's also acting down here with another t, so that is going to be an area, a cross-sectional area that we're dealing with here of 2 times t, double that thickness for the top and the bottom right there, times our delta x, which is our width right there. So that's the first force. What other force do we have acting? Well, we have our p times dA right there. We have our P now right here, and now we have this area right here. So if we look at this, what is our area of this rectangle right here? Well, it has a delta x width, it has an R and another R right there. So that's 2 times R times our delta x will give us the cross-sectional area of that face there. So we can set those equal to each other now because this right here is all equal to 0. So now we can say our sigma 1 times our 2t delta x is equal to our p times our 2r delta x right there. Well, we can divide this over here by this right here. So if we divide on this side right here by 2t times our delta x right there, well, what cancels? Well, our 2 cancels and our delta x cancels. So we're now left with that sigma 1 is equal to our pr over t, which is exactly what we have right here. And this is shown in our textbook as equation 7.30. So now let's take a look at our longitudinal stress. If we go back to our diagram up above here, we can see now we're dealing with our sigma 2 right there, which our sigma 2 was our longitudinal stress for our cylindrical vessel with principal stresses. So we can come down and draw our free body diagram to determine our longitudinal stress. We draw this out and we can see we have one force here acting in our x direction of a sigma 2 dA and another force here of our p dA acting in that x direction as well. We see this distance out here. This is our radius r right there. So from this here, we can go back up to our equilibrium equation, say summation of forces in our x direction is equal to 0. So what forces are acting in our x direction? Well, let's deal with this force first. This is our sigma 2 dA. So our dA is the cross-sectional area around this lip here with a thickness of t. So this is going to be 2 pi r times t for that area, our dA right there for the surface area. So we have our sigma 2 times 2 pi rt. And now we have our pdA. Well, for this right here, that's just the circle on the inside of there, which is the area of a circle is pi r squared. So there's our pi r squared right there. So it's p times pi r squared for that force. Now this is our equilibrium equation. This is equal to 0. So we can move this over and now say that this right here is equal to that there. We're going to move things around a little bit. So we want to solve this for our sigma 2. So we can divide both sides by this 2 pi rt. So we'll draw this down on the bottom here. That's our 2 times our pi times our r times our t there. Well, let's take and cancel things out. We can see that our squared cancels with our r here. So that's r's gone. Our pi cancels with our pi here. So now we're left with the fact that sigma 2 is equal to PR over 2T, which is this relationship that we have right here. Sigma 2 is equal to PR over 2T. And again, that comes from our free body diagram, equilibrium equation, rearranging and simplifying, and we come up with our equation 7.31. So now we can see that there's going to be a relationship between our sigma 1 and our sigma 2 right there. So we can see that we have a PRT for sigma 1 and a PR over 2T for our sigma 2. So our relationship between those is just that 2 on the bottom there. So we can say that sigma 1 is equal to 2 times our sigma 2, which is given in our relationship shown in equation 7.32 in our textbook. So continuing to look at the stresses in the thin-walled pressure vessels, we can now take a look and bring back Moore's circles. Here on the left is Moore's circle for an element of a cylindrical pressure vessel. So we left this in general terms right here, and we see we have these points A and B correspond to our hoop stress, sigma 1 and sigma 2. So there is our B right there, And there is our A right there. So we can see now we had that relationship between sigma 1 and sigma 2, that sigma 1 is equal to 2 times our sigma 2. So sigma 1 is this full distance from our point here at O, the origin there, all the way out to our point A right there. So the full diameter of that Mohr circle is our sigma 1. And we just proved that our sigma 1 is 2 times our sigma 2. So we go right here to our point B right there, and we can show this is our sigma 2, which goes from O to B, and the same sigma 2 from B to A right there. So if we know that this is sigma 2 is the diameter of this smaller inner circle and this smaller inner circle there, switch my highlighter between this smaller inner circle, our whole diameter of this is our sigma 2, and for this circle here, our whole diameter of this is our sigma 2, then we know that the diameter goes across this here from E to D right there is going to be a sigma 2 as well. So if we cut that in half along our sigma line right there, then this distance from that line, our O line right there, our midplane line, is going to be this 1/2 of our sigma 2. And this is what we refer to as over here our maximum in-plane shearing stress, or our tau max in plane. And this is that 1/2 sigma 2, which comes directly from that right there. Now this is also equal to, we can see from our previous derivations on the slide before this, and also from our equation 7.33 in our textbook, we can plug in this for our value for sigma 2. And if we have that value for sigma 2 here, we got 2 times 2 is equal to 4. So then we're left with our tau max for in plane is equal to our PR over 4T. So that's relating our tau max back to our sigma 2, which is our longitudinal stress, and our definition for sigma 2 that we can plug in for that, take half of it, and we end up with this PR over 4T from equation 7.33. So that was for our maximum in-plane shearing stress. If we want to look at our maximum out-of-plane shearing stress, this corresponds to a 45-degree rotation of the plane stress element around our longitudinal axis. So this is our T max right here. So if we know this whole diameter right here is our sigma 1, then we know that this distance from our point B to point D prime right there, which is our tau max, this is going to be equal to half of sigma 1. Well, half of sigma 1 would be half of 2 times sigma 2, which would be our radius of this circle right here, our sigma 2. So we can say for our maximum out-of-plane shearing stress, our tau max is equal to our sigma 2, which we have a definition for sigma 2 that we showed earlier. This is our PR over 2T, which is now our relationship here in equation 7.34 in our textbook, showing us that our tau max is equal to that sigma 2, or our longitudinal stress. So as we wrap up our section on our stresses in thin-walled pressure vessels, we want to take a look at another shape. Now we're going to take a look at a spherical pressure vessel. So we have this pressurized spherical vessel here, and what we can see in this is we have our sigma 1 and our sigma 2 here, but regardless of which direction each one of these in, they're going to be equal to each other. It's a sphere. No matter how we cut it down the middle, it's going to be the same. So our sigma 1 is going to be equal to our sigma 2, so we can still cut this in half and do out our free body diagram. So that's what we do. In this relationship, we can see we have free body diagram to determine our spherical pressure vessel stresses. So we cut it in half, say, okay, what are our forces? So we're going to do an equilibrium equation now from our free body diagram. So for our free body diagram, we see we have our sigma 2 times dA force and our P times our dA right there. And we're going to do our summation of forces in our x direction. So summation of forces in our x direction is equal to 0. So we can see we have our sigma 2 times our dA. So that dA is still that cross-sectional area around that lip right there. So we can see this is going to be 2 pi r times that thickness T right there. And we have down here our PdA, where our dA here is just the area of a circle. So this is pi r squared. So this is P times our pi r squared. So this is the same as we saw before. So we can set this equal to this because these are both that minus that is equal to 0. So set these two equal to each other. And then we can solve for our sigma 2. And when we do that, we again move things over. We can cancel it out. And what we're left with is that our sigma 2 is equal to PR over 2T. So that's where this relationship here from 7.36 in our textbook comes from. We have sigma 1 is equal to sigma 2 is equal to PR over 2T. So now the difference here between our spherical and our cylindrical is that we don't have this hoop and longitudinal, and our sigma 1 and our sigma 2 are equal when we're dealing with a spherical pressure vessel. Let's now take a look at Mohr's circle for element of a spherical pressure vessel. So we have this diagram down here. There's our sigma, there's our tau for Mohr's circle. We can see we have our origin point here. We have our point A out there, where this is our sigma 1 is equal to sigma 2 that we showed in this relationship in equation 7.36. So what we can do now is look at Mohr's circle and say for an in-plane transformation, this is going to reduce to a point. So our sigma is equal to sigma 1 is equal to sigma 2 is equal to a constant right there. And this relationship is given in our equation 7.35. So with this case here, that means that our tau max for in-plane is going to be equal to 0. But for our out of plane shearing stress, we can come over here and see that our tau max here for out of plane, this is going to be the radius of this circle to go from there up to our point D prime right there. So that would be half of our sigma 1 or half of our sigma 2 right there. So we can say we have this relationship that we can show in 7.37 that our tau max is equal to 1/2 of our sigma 1, and we had a relationship for sigma 1 up here, which is PR over 2T. So half of PR over 2T would be PR over 4T. So that's where we get that relationship in 7.37 for our maximum out of plane shearing stress. So let's apply some of that theory and governing equations to an example problem. Let's take a look at sample problem 7.4 from our textbook. In this problem, it tells us that the state of plane stress shown here occurs at a critical point of a steel machine component. So they're telling us the component's made of steel, and we're dealing with a plane stress right here. So as a result of several tensile tests, the tensile yield strength is known to us and given to us as sigma y is equal to 250 megapascals for the grade of steel that they've used. Now within this problem, they're asking us to solve for a couple different things. They want us to determine the factor of safety with respect to the yield using two different things. A, the maximum shearing stress criterion, and B, the maximum distortion energy criterion. So solve for the same thing in two different ways. We're trying to find this factor of safety with respect to our yield using both our maximum shearing stress and our maximum distortion energy criterion. So now that we've had the opportunity to read through that problem statement and gather an idea of what they're asking us to do in this problem, our next step, if we were solving this out by hand, would be to create our setup page. So again, on our setup page, you recall we have all of the given information, everything they're asking us to solve for, and any assumptions that we're going to make. So once we have that information, we can then reference back to that page there in order to create our procedure for analysis or our strategy. Now we can see our strategy here is that we're going to draw a Mohr's circle from the given state of plane stress. So this is our given state of plane stress they gave us in that diagram within the problem statement. And we're going to analyze the circle to obtain the principal stresses and our maximum shearing stress. From there, we can then apply those two criteria in there, our maximum shearing stress and our maximum distortion energy criteria, in order to solve both ways what they asked us to do in the problem for that safety factor. So for our modeling and analysis, in order to create Mohr's circle, what we want to do is take a look back at this given stress element right here from our problem statement. Now we can see that we have our general equation here for our average stress right there. Our average normal stress is given to us as that distance OC, or half of sigma x plus our sigma y. Well, we do have our sigma x and our sigma y. So we come down to this diagram here. There's our x direction right there. There's our sigma x right here. There's our sigma y right there. So we can see our sigma x is going a positive 80 megapascals, and our sigma y, according to our chosen coordinate system here, where x is positive to the right and our y is positive going up, that means that this 40 megapascals right here is going to be a negative. So for our sigma average right here, this is going to be 1/2 of our sigma x, which is 80, plus our sigma y, which is a negative 40, which is again where that sign convention came in right there. So we say 80 minus 40 is 40 divided by 2 from that 1/2. So now we get our sigma average is equal to 20 megapascals. So now if we want to find our maximum shear stress, or tau sub m, what we can do is we can realize that that is the distance from C to D right here, which is the radius of our circle. So that's why we say this is equal to R right here, and we realize if this right here is our radius, then right here from C to X is also our radius that we're labeled R right here. So that's what we say our tau sub m is the same as equal to our R, or radius of that circle anywhere. So from that relationship there, we can then say, well, we've got this right angle over here. We got this right triangle right here. We go from C to F, and then from F to X, we can say, well, from Pythagoras' theorem, our hypotenuse is equal to the square root of the sum of the squares. So if we take our CF in green there squared plus our FX in red there squared and take the square root of that, that will give us our hypotenuse right here, or our radius for this circle. So we can take a look at this and we can say, okay, well, what do we know? Well, our Fx is pretty straightforward. Fx, that is our shear coming right from here. That's 25 megapascals. That's where this relationship comes from for our Fx when we draw out Mohr's circle right there. Now we need to say, what is our Cf? Well, if our Cf right here, now we need to figure that out. So it's a little bit complicated, but not too crazy, and we can still get this just by taking a look at two of the different dimensions of our Mohr's circle. So what we can do with that is we can say, okay, well, we can see that our sigma x right here is 80 megapascals. So if we come out from our point O right here out to our point F, this is going to be our 80 right there. We've also already calculated that our sigma average right there was 20 megapascals by looking at 1/2 of the sum of our sigma x and sigma y, taking the average of those right there. So that's that 20 right there from O to C. So if we have those two right there and we see that this total distance is 80 and this distance is 20, then 80 minus 20 would give us our CF distance of 60. So we can write this in right there as our CF right there is 60. And then we say, okay, well, our fx right here is 25, so 60 squared plus 25 squared square root will give us our tau max right here of 65 megapascals. So now that we've calculated that our radius is 65, that means that our total diameter of the circle is going to be double that, so 130 megapascals for our total circle. So our sigma b, which is our minimum, and our sigma a, which is our maximum, is going to be a total, when we add those together, of 130 megapascals. So this tells us a little bit more information. So again, we're trying to derive all of this information just from these dimensions on Moore's circle right here. So let's take a look at this here. So now that we know that from C to F is 60, but we also now know that from C to A is 65, because that is the radius. Like I said, that radius from C to D, C to X, C to A, C to B, anywhere on the outside, even C to Y over there, is going to be that value of 65 megapascals, which is our radius right there. So now what we can do is we can go down to the bottom. If we wanted to find our sigma A right there, we can say, well, sigma A is the sum of from O to C, and then from C to A out here. So from O to C, that's 20 megapascals right there. And then from our C to our A, well, that's our radius right there, and that is 65 megapascals, which now gives us a value for CA is equal to 85 megapascals. Now we can do the same thing over here to go for our sigma B. So we go again here, well, we know if B to C is that radius right there, so that is 65 right there. So we can say if we want our sigma B right here, well, what we can do is we can subtract our OC from our BC right there. So OC, which is our value right here of 20 minus our 65 right there, would be 20 minus 65, or a negative 45 degrees for our sigma min or our sigma B right there. So now going back to our setup page and our initial problem statement, we recall they asked us to solve two different ways for our factor of safety right here. The first thing that asked us to use is maximum shearing stress criteria. So with this here, since the tensile strength right here is given to us in the problem statement that our sigma y is 250 megapascals, then the corresponding shear stress at yield we can find by this relationship here that we saw earlier in the lecture that I boxed in over here, that our tau sub y right here, the shearing stress at yield, is equal to 1/2 our sigma y. So we can just plug this in as 1/2 of 250 megapascals gives us 125 megapascals. Now we've solved previously here that our tau sub m, our maximum shear stress, is 65 megapascals already. So if we take a look and recall back for our factor of safety, we can simply say that this is our tau y over our tau m, or 125 over our 65 right there. So therefore our factor of safety is a 1.92 for this problem. So now they wanted us to solve a different way utilizing the maximum distortion energy criterion. So we can go to our equation 7.26 and introduce this factor of safety into this equation here. So we have this governing equation now from 7.26 in our textbook, that our sigma a squared minus our sigma a times sigma b plus our sigma b squared is equal to our sigma y over our fs squared right there. So a little bit more complicated formula here. We can see that our sigma A, if we go back there, that was our 85 that we shown from our Moore circle there. Our sigma B was a negative 45 that we shown as well. So we had both of those, our sigma A and B, as our principal stresses right there. So I've recalled these out there. And now we have our sigma Y was given to us as 250 megapascals right there. So we can plug that in there. Our sigma A is the 85. Our sigma A, 85, sigma B, negative 45, our sigma B, negative 45. We're squaring that so the negative goes away. Then we had our sigma Y, which is given to us in the problem statement as 250, all over our factor of safety right there. So that's our only unknown, one equation, one unknown. We end up doing the math out over here. We say that 114.3 is equal to 250 over our factor of safety. So we solve that out, and our factor of safety from our maximum distortion energy criterion ends up being 2.19. So one thing that we notice here is there is a slight difference between our answers, whether we're using our maximum shearing stress criterion or our maximum distortion energy criterion here. Where we had our FS for our maximum shear was 1.92, and our FS from our maximum distortion energy criterion was a 2.19. So as we're thinking about this, let's think about our problem in general here. We had a ductile material. They gave us our sigma sub y of 250 megapascals. Now from that, what we can do is we can draw a hexagon associated with the maximum shearing stress criterion right there, and an ellipse associated with our maximum distortion energy criterion. So we can do that out, and we end up with this diagram that we see down below here. So the given state of stress is represented by point H. So there's our point H right there. With the coordinates here, we can see if we go over 85 in our sigma A direction, and we go down 45 in our sigma B direction right there. And we calculated those previously in this problem right there. So we have those two values, and those represents our coordinate system for our OH right there. Now the straight line that's drawn through points O and H, so if we draw a straight line through point O to H right there, this is going to intersect the hexagon, if we keep going out here at point T, and it's going to intersect the ellipse here if we keep going out at point M. So this is a straight line that goes straight through from O to H, and we can extend it out, hits our hexagon there, hits our ellipse right there at point M. So for each of these criterion, our factor of safety is verified by measuring the line segments indicated and then computing the ratio. So let's take a look at our maximum shearing stress criterion first. This side here says our factor of safety is equal to OT divided by OH. So OT right there divided by our OH right there will give us that value right here. Now we can go through and calculate each of these out. We know our distances based off of our sigma y's right there, so we can figure out exactly what those are. So from O to H, we could take and say that's the square root of the sum of the squares of our 45 and our 85 right there, and we could calculate that distance for our OH right there. And then we could do the same thing if we wanted to go from O to T right there and figure out that value right there, and we find that ratio, that ends up being our 1.92. Now for our maximum distortion energy, we go out here to our point M right here. You see that's a little bit further out on our ellipse at this point right there. So if we go out to that point M, that OM is going to be slightly larger than our OT right there. And we can see that just because one's a hexagon, one's an ellipse right there. And we do that out, and that comes out to our value of 2.19.